Your stress. Can you go right?
Okay, let's get started.
And told us about it 3 months today.
Let me have your attention. Let's get started. It's my privilege to welcome you to the University of Tennessee Nuclear Engineering Department Seminar Program. Today's speaker is Mr. Richard Rawl, who is the Senior R&D Program Manager of the Transportation Technologies Group of the Oak Ridge National Laboratory. Richard has been with ORNL for 15 years. Previously, he worked for the International Atomic Energy Agency and also with the Department of Transportation. He holds a BS degree in Chemical Engineering with an option in Nuclear Engineering from Virginia Tech and an MS degree in Industrial Engineering from the University of Tennessee. So, it's my privilege to welcome you. Thank you for coming.
Thank you, Dr. Dodds. It's good to see so many nuclear engineers and nuclear engineers in the making. But, you know, you study about reactors and facilities that use radioactive materials and produce radioactive materials. And how much do you think about how it either gets there or how it gets to where it's going? Probably very little. There are a lot of incidents involving radiological materials, but if you think about it, you'll think back and see there are very few that are transportation incidents that involve radiological materials. It's an activity somewhat going on in the background, and most of the time we don't think about it. But some people are very concerned about it, especially when it deals with certain materials. First, a word from our sponsor, shameless plug. I'm with the Nuclear Safety and Technology Division at ORNL, Transportation Technologies Group, and we specialize in radioactive materials, packaging, and transportation. And we're now located at the new National Transportation Research Center, which is just across the Pellissippi Parkway from Pellissippi State. So if you get in the vicinity, stop by and visit. We have a package testing lab where we do package testing, everything from drop testing to compression testing, certification of packages, and many things that are related to the safety and security of radioactive materials. So come by and see us if you get a chance. You probably are aware that radioactive materials are very widespread in our everyday life. There are consumer products that contain small amounts, such as smoke detectors and static eliminators that are used in Xerox machines. There are medical applications that are used very widely now. Nuclear-based diagnosis and treatment techniques will be performed 10 to 12 million times each year in the United States. In the industry itself, there's non-destructive examination or radiography that goes on a variety of important materials applications, including such things as gauging materials that are being manufactured, sterilization of contact lens solution, bandages, well logging in the oil industry, a variety of applications. And then in the energy sector, we're familiar with nuclear power generation, which requires the transportation of fresh fuel to the reactor, the transportation of spent fuel eventually from the reactor, and the wastes that are generated as well. There are thousands of shipments of materials made every day. Almost 3 million shipments per year in the United States, which equates to nearly 3,000 shipments of radioactive materials on our highways, waterways, and in the air every day. Most shipments involve smaller quantities, the consumer commodities, the nuclear medicines, but there are a number of shipments that do include the larger quantities of activity. New applications are being invented every day for the application of nuclear technologies, especially in the medical and the imaging industries. And there are projected increases to occur as a result of the Department of Energy beginning to transport more of their wastes, as well as commercial spent fuel. Right now there is a licensing application for a commercial spent fuel storage facility in the West, and if that becomes operational, spent fuel will move to it from the utilities that are partnering in its generation. And there's another activity, which is the creation of the repository in Yucca Mountain. But everybody knows that transportation accidents will happen. The predicted frequencies for these events is low, but they're finite. People know that accidents are going to occur. We all know that. And hazardous materials accidents make the headlines. When one does occur, it usually is big news, especially like a train derailment such as this, which involved some anhydrous ammonia. It was in a headline getting activity. The spills and leaks can be deadly, and there's a lot of concern that exists because people associate this with transportation. These are some of the headlines that I just pulled down off of the internet. You can go there and find hundreds of them. A press release from Public Citizen just last month. Demonstrators at Capitol protest dangerous nuclear waste transportation plan. In Argentina, there was a headline of an article in one of the newspapers, The Death Ship, referring to shipments of 55 high-level waste that would be passing along the coasts of South America on its way to Japan. And then in the Washington Post recently, realizing anything could happen, experts prepare for the worst. So people's concern is oftentimes somewhat affected by what they see and what they read regarding this topic. But what do the experts say? Well, the transportation of radioactive materials has been studied and risk assessments have been performed since the inception practically. Beginning in 1977, the Nuclear Regulatory Commission undertook a comprehensive environmental impact assessment of transporting radioactive materials in the U.S. Their conclusion was the radiological risk from accidents in transportation is small. That report was recently reviewed two different times, in the in the early 1990s and recently in the year 2000. The most recent one, which was done by Sandia, I'm hitting the wrong button here, which was done by Sandia, which is a re-examination of the spent fuel shipment risk estimates that were included in NUREG 0170, showed that the results of the original study were very conservative, meaning that the actual risks as calculated using more modern methodologies were lower. And then on the international scene, the International Atomic Energy Agency's General Conference, which is the conference that's attended by all the member states, concluded themselves that compliance with regulations that are based on the IAEA's regulations is providing a high level of safety. So we've got a real dichotomy of opinions between the risk assessments and what those experts say, what the politicians are saying at the international arena, and what's going on in many people's minds. So what's all the fuss? Well, I think we know pretty well that radiation is scary to most people. It's undetectable without instrumentation, and it does make the headlines. Many people have an inherent mistrust of technology. Transporting radioactive materials involves some technology. We're all familiar with the high visibility failures, catastrophic failures where the technology has not done as performed, such as the Challenger disaster. There are also visible and sometimes hidden agendas on both sides. Sometimes you have the nuclear industry taking one side of the issue and those that are against nuclear power on the other side. And that can lead to a very polarized and somewhat self-serving dialogue on the matter. And both sides, in most cases, think they're right. But how hazardous are the materials? Radioactive materials, when you look at the entire spectrum, covers an almost incomprehensible variety of hazards. The quantities of material that are transported, the physical amounts, vary from minuscule to very large, from tens of becquerels, which is barely anything we would consider radioactive, to tens of petabecquerels, 10 to the 16th. So we're talking 16 orders of magnitude difference between the smallest quantities that may be shipped and the largest. The radionuclides themselves, the dose per unit activity spans 5 orders of magnitude, so that the dose I would receive from inhaling, say, a microcurie of actinium-227 is 5 orders of magnitude higher than the dose of that same activity of tritium. And all of these hazards need to be appropriately and adequately addressed in specifying safe transport regulations. Physical forms vary, everything from gases to liquids to indispersible solids. The chemical forms vary, all the way from inert materials such as noble gases to highly reactive chemical forms, which would be dangerous when exposed to the atmosphere because they would react with the moisture, or they may be pyrophoric. So the hazards range from insignificant to very significant, and yet we've got to specify a set of regulations that will allow all of these to be transported safely. It's quite a challenge. The original formulators of the regulations sat down and came up with what I think was a rather brilliant set of observations. And if you take radioactive materials, there are only 4 things that you need to do to safely allow the transportation. And those 4 things are relatively simple. First, keep the goods in something. Provide containment. Don't allow it to be dispersed. Once it's contained, it's easily dealt with. Second, provide shielding. For hard gamma emitting radionuclides, you may still have them in a containment, but unless it's shielded, it presents a radiation hazard. Criticality. Some special radionuclides can undergo nuclear fission. If we keep them apart in masses that are subcritical, that particular hazard can be prevented as well. And heat management. Some quantities of radionuclides, such as plutonium-238, a small quantity can generate a lot of heat. And if you think about all the hazards that radioactive materials can present, those 4 simple principles are all that's needed to safely allow it to be dealt with. So, exactly how does one do that? Well, I thought we'd have a little test here. We'll see if we can do this. Now, what I've got here is a radioactive egg. Let's pretend it's radioactive anyway, okay? And I'd like to see us transport it. I'd like to give it to this gentleman and have him hand it all the way back to the back of the room, across the room, and back down the front. Now, in case we have a problem, I've got an emergency spill management kit here, but please don't drop the egg. Okay? And I'm going to time it, see how long it takes us to transport it. Ready? Go. And it's being handled carefully, from one to another.
Hand it to you.
All right, we safely transported it in 25 seconds. But how could we transport it either more safely or quicker? Okay, we did it in 25. How safe did you feel handling this? Very safe? Kind of what happens if I drop this thing? Am I going to get blamed for it? And it was 25 seconds, but it took a few handoffs. So how could we do it more safely? I'll just throw out some suggestions. Single carrier. I could hand it to one person and have them run the route, right? But that's more costly and it's going to involve specialized carriers. How about if we told everyone to hand it off more slowly and more surely? Well, that would be safer, but it'd take longer. How about if we had everyone go to a training exercise on how to handle eggs? Well, it'll probably work as well. Any other suggestions on how we might do it more easily, or quicker, or safer? Package it better. Okay, another challenge. I can pick on you. Can I pick on you? Do I have a volunteer, I should say? No volunteer?
The guy in the blue shirt, he's a real good
Okay, come on down. Let's see if we can actually do it. Okay, here's your packaging, high-density packaging material, low-density packaging material, and the contents, okay? And an outer package, and I'll even help seal it up and stuff.
Can you put it in here?
Yeah. We'll do it. So we've got containment now. We don't need our shielding. It's not fissile.
It doesn't go pretty.
It has no heat. All right, let's do the same exercise. See if we can get it done faster. Ready? Got a long pass.
Hard to say, y'all throw it to me. I catch it.
12 seconds. Half. So a few simple precautions such as packaging the material properly can really lead to great improvements in the ability to handle it safely and handle it quickly. The key is in the packaging, and that's the principle on which the materials, the radioactive regulations were first developed. Those first regulations were formulated in the international community in 1961. So we've got over 40 years of experience in developing the regulations, and they were published by the International Atomic Energy Agency. It was one of the very first publications they did. When it was formed by the United Nations, one of the first activities they were given responsibility for were to come up with a set of standards for transporting radioactive materials, because remember, 1961, nuclear power was really on the rise. Those regulations are published by the IAEA. They're adopted by the United Nations Committee on the Transport of Dangerous Goods. They're implemented by convention, such as the Chicago Convention internationally, and it's binding international law on countries, including the United States. And then regulations that are consistent with all of those are incorporated into the federal regulations of the Department of Transportation and the Nuclear Regulatory Commission. So if you don't think there are a lot of regulations telling you precisely how to transport radioactive materials, just take one of those to bed at night. See how fast you go to sleep reading it. They are quite detailed. Those regulations back then started building on the principle that the shipper could best provide appropriate protection, and that's still the approach that's taken today. The shipper knows best the material that he has and its hazards, and can provide the appropriate level of protection in accordance with what the regulations require. The regulations minimize the need for carriers to take actions. If you've shipped anything on a common carrier by the highway or the rails, you know you don't want the carrier to have to do very much. So that principle has been built into the regulations and continues to be there. That way the safety during transportation is as passive as possible. Now, in order to make the packaging commensurate with that wide variety of hazards, they had to come up with a scheme on how to do this. So the first thing to do is define what's radioactive for transportation purposes. The definition is 70 becquerels per gram. That way dead bodies don't have to go into lead-lined coffins. I mean, we are radioactive, but not what we would normally think is sufficient to be warranting transportation requirements. Limited quantity, these are very minor hazard things, such as smoke detectors. Low specific activity materials have low activity concentrations. Dirt, for example, has a low activity concentration, but if it has sufficient uranium and thorium materials into it, it would be regulated. It's greater than 70 becquerels per gram. The next quantity up is type A quantities. Of course, you know, every regulatory regime has to have its own acronym, so it's got type A quantities to indicate moderate hazards, type B quantities to indicate significant hazards, hazards that are so significant that protection is needed even in the event of severe transportation accidents. And there's a new category that will be coming into the U.S. regulations perhaps soon. It's in the IAEA regulations now that deals with type C. And those are quantities of material that when they're transported by aircraft, it was felt like they needed to be protected against even in a severe aircraft accident. Most of these packages are type A or less. The vast majority are the small quantities. The consumer products, samples, specimens, the ores and concentrates are typically Ores and concentrates typically shipped as LSA, and all they need to do is withstand the routine conditions of transport. They're not going to be a significant hazard if they're in an accident, but just get them there in one piece is basically all the safety that's needed for them because of their limited hazard. And nuclear medicines are typical Type A packages, and those we expect to be protected against minor mishaps, dropping it off the loading dock, for example. The Type A requirements includes contents that are limited. There's a specific amount of material you can put into a Type A package based on whether it's dispersible or not. And that limits the potential consequences in the event of a release. They won't withstand accidents, they'll withstand normal routine handling, but if there is an accident, the consequences are limited because the activity inside is limited. And the external radiation levels are limited as well. Typically 2 millisieverts per hour to package surface, and a tenth at 1 meter. So there is a requirement for shielding as well as containment. Now, the Type A package tests, which demonstrate the ability to withstand normal transport and minor mishaps, is a water spray, which simulates rainfall, letting it sit out on a loading dock. Free drop, 1.2 meters, it might get rained on and then dropped off the loading dock. A stacking test, which indicates that when it's in storage, it may well have other packages placed on top of it. Penetration test, which actually, if it was going to be rigorous, would probably be a forklift time, but no, the drop of the bar on it simulates a penetration event that's expected to be withstood. And then for liquids and gases, there are additional requirements because they're even more dispersible than dispersible solids. And as a result of these minor mishaps, once you subject the packages to these tests, there can be no release and no significant increase in radiation levels. But what about the real dangerous stuff? Okay, that's the Type A quantities, the nuclear medicines. What about the stuff that's really hazardous? Well, that has to go into what's called the Type B packages, and they're designed to withstand severe accidents. The accident conditions were studied originally back in the 1960s, and they were used to set the standards that have been re-examined ever since. We're continuously looking at the latest transportation accident statistics in order to determine if new tests are needed, and they have been added over the decades since the 60s. The performance tests have been periodically updated. Deep immersion test has been added. The severe aircraft accident test has been added, a dynamic crush test. So the regulations are dynamic. And all modes of transport are included in this set of regulations. Highway, air, rail, and most air accidents are included within the Type B. The test requirements for Type B include the cumulative effect of sequentially performed tests. First, there's an impact test, and the impact is a 9-meter drop. I keep pushing the wrong button, but the 9-meter drop onto an unyielding target in the most damaging orientation. I'll explain that a little bit more. Or if the package weighs less than 500 kilograms, if it's lightweight, then you have to drop 500 kilograms onto the package. So it depends on which is more damaging, if the free drop is more damaging or the crush test. The penetration test is where the package is dropped onto a penetrating bar, and that's designed to simulate something like a broken rail in a railroad accident. The thermal test, fire test of 800 degrees C with a heat flux equivalent to that of a fully engulfing hydrocarbon air pool fire with specified flame emissivity and surface absorptivity. And that's roughly about how long it takes 5,000 gallons of fuel to burn. And water immersion. There's two different water immersion tests for the higher activity packages. It has to be subjected to 200 meters. An hour was chosen because if it'll survive an hour, it'll survive a week. I mean, the water immersion is essentially a crush test. And that's intended for packages that are Type B with high activity to be salvageable off of the continental shelf. So it could be recovered without being a significant hazard to those doing the recovery. And Type C packages for the severe aircraft accidents have more stringent requirements. 90 meters per second. You can't get there with terminal velocity. You basically have to pull the package down or fire the package into the impact surface to reach 90 meters per second. a puncture tearing test where the package is actually dropped onto or has a probe dropped onto it that's designed to tear the outside of the package to make it more vulnerable to further damage. A thermal test is for 60 minutes, and the immersion test is the same as for the high-activity Type B. But this is to illustrate that the accident forces that could be seen in real accidents are being replicated in a series of engineering specifications. Now, why only a 9-meter drop? You may have heard this argument before. If you follow people's arguments why transportation is not safe, this is one of the first points that's made. 9 meters provides an impact velocity of only about 30 miles per hour. How could that be safe? Trucks are traveling down the highway at 80 miles per hour. Well, that's probably a good illustration of the problem that I think is most faced in this whole regime. Many people think of the worst case accident. What's the worst accident I can think of? Well, if you look at the probability distribution of accidents, it's got a traditional, very tapered curve. If you go out in more and more remote probability, the accident forces can get fairly high. But you quickly start getting into the difference between what's the absolute worst case accident versus a severe accident. What's possible rather than what's probable. We can always think of a series of events that borders on the impossible because it is so improbable, but it could happen. And this is where I think a lot of people have their disconnect between what the regulations are addressing, which is making sure that these packages categorically will survive severe accidents, versus thinking up a worse scenario that just might reach that package. And that is probably the point of most debate. But it's just I guess a fact to recognize that the regulations deal with severe accidents, and they're sufficiently far out on the tail end of the curve that the regulatory authorities have concluded that anything beyond that is improbable. The unyielding target effect is not intuitive. Remember, this was an engineering specification. There are not very many unyielding targets in the real world. But from an engineering standpoint, it's perfect. It's perfectly reproducible. I could test that package every time on that same unyielding surface, and I will get the same result, because the impacting surface does not enter into the damage. Its behavior doesn't enter into the damage. The damage is done to the package. The most damaging orientation is also not very intuitive. Whereas the package is traveling down the highway, it doesn't matter how its orientation when it's traveling. When it's tested against the regulatory test, if you have to turn it upside down and drop it backwards, if that's the most damaging orientation, you have to test it that way. And then the unyielding surface and the 9-meter drop also takes no account of loss due to crushing of the vehicles, translation and rotation of the vehicles, the dynamic accident forces that are always present. If you crash two trucks head-on at 80 miles each, you're going to have a tremendous amount of energy that goes into crush, translation, rotation, lift. How much energy goes into the package? Well, I've got some tests later on that show a little bit about that. So the Type B tests are reproducible, and they're intended to result in damage that's representative of severe real-world accidents. The unyielding target. Now here's a picture. Hey guys, I had to think up a caption for it. You know, I had a package around here somewhere. They tested a package on an unyielding target. Then they took it about 2,000 feet in the air and dropped it onto what's called desert hard pan soil. I don't know exactly what that is because I've lived on the East Coast all my life. But they tell me it's almost like concrete. They dropped it from 2,000 feet. They had to dig the package out of the hole, and the damage done to it was less than what the 9-meter drop had done to it because of the difference of the targets. The damage, as it ends up, is related to the relative stiffness of the package and the target. And most Type B packages are stiff, so it requires an extremely stiff target for it to begin to damage the package rather than the package damaging the target. Now, how do we determine what the risk of transporting the materials may be? There are 4 components to risk, and this is what the regulatory agencies need to address and look at in order to communicate effectively, to quantify what the real risk of transporting it is. They're incident-free risks. Just as you're putting a package on a truck and you're driving down the highway, you're creating emissions. Nothing's going on, but the physical fact that you're moving is creating an impact. And then there's exposure to radiation coming from the package. You know, packages that have gamma emitters in them, they're going to have some radiation level around the package. The driver, people in adjoining vehicles, they will be exposed to some very small level of radiation, but it will occur. And then there are accident-related risks. Injuries and deaths due to the mechanical forces or thermal forces of an accident, as well as potential radiological impacts from releases. And how do you determine that risk? Well, almost every type of approach has been used to quantify the risk. Event trees that lay out all the sequencing of activities that could occur, as well as looking at how those affect the packages. One has to come up with, given that accident occurs, what is the response of the package? And that has to be predicted. When that's predicted, one can calculate what are the release fractions, how much of the material might get out of the package, what are the conditions of the release, the location of it, the population in the area, the weather, whatever. These all have to be assumed in order to perform the risk calculations. Then the consequences can be determined. Since we know the probabilities, we can then calculate what the risk is. And what's been determined since that first study in the U.S., that New Reg 0170 back in 1977, is that the risk, the consequences from less than type B quantities, since the activity is limited, is small. And the performance of type B contents packages, because they are resistant to severe accidents, is also small. But the result of the risk assessments is coming up with great numbers, like mean accident population dose risks from a single shipment of spent fuel. Now, I don't know about you, but I don't get a whole lot out of that. I have to study the diagrams quite a few times to get an idea of what's going on. But the main point is that based in 1977, they made some conservative assumptions. And the calculated mean accident population dose risk has dropped, look at that, almost 4 orders of magnitude, based on better modeling of the package response, the contents release, and the consequences once that release is assumed. And by truck and rail, it varies. But the numbers have all been calculated to a great degree. They just don't really do much to communicate to the public whether this is safe or not. And the controversy, consequently, is going to grow. The Department of Energy and the President have recommended to Congress that Yucca Mountain is suitable to proceed to the NRC for licensing as a repository. And the state of Nevada has already said, that's it. We don't agree with that whatsoever. We want to fight this. They've already passed their veto, I believe, that says Congress has to override it. And Nevada has come out and said they're going to focus on transportation. They feel that that's their best way to involve the other states, to get them on their side with the fact that this is not a good idea to have a repository. Nevada doesn't like it because it's in their state. They don't think anybody else should like it because it may involve transporting spent fuel through their state. And they're trying to raise $10 million. And on the website, the governor was sort of criticizing the industry in the Las Vegas area for not ponying up to the $10 million table fast enough. So they have in mind a national television commercial campaign against transportation. And if in the next 6 months, we'll probably be hearing that because they want Congress to override the President's recommendation. And if Congress doesn't, we'll probably be hearing about it for the next 10 years as the repository goes through the licensing process. You can go onto a number of websites and find out where the shipments are going, where to see them. Uh-oh, I clicked another button and it's... Okay. And as you can see, even... Uh-oh. There must have been a file in there that... Okay. But we can even see over here, I'm probably doing it at the same time. Just look through Tennessee. We can see it coming out of North Carolina, heading across I-40, getting to Knoxville, and heading right up 75. So there will be activities directed towards getting everybody along the routes involved to be concerned about these transportation activities.
Am I reading that? It's a railroad that comes to us, right?
I think that was highway.
Well, that's a... It said rail.
Okay. All right, I'm sorry, you're correct. The red is the rail. So it's CSX, not Southern Cross. They look really like the interstate system. But we can expect the controversy is going to grow rather than quiet down. So the question is in many people's mind, is spent fuel packaged adequately for safe transport? Well, this is just an example of what a... This is just the example of what a spent fuel cask looks like. They are massive structures. Most of them are steel outer walls, lead or uranium shielding, steel inner walls. Some of them are monolithic steel, but they are massive structures, most of which are fitted with impact limiters, and they're rather robust. They have to meet all of those Type B accident tests and to be certified by the NRC. So not only do you have to do the tests on the package yourself, but you have to prove to an independent regulatory agency that you've done it properly. Now, because of the concerns over spent fuel transport, the U.S. and the U.K. both have sponsored extra severe regulatory tests, where they said, okay, you know, we know the regulatory agencies have confidence in the tests. Well, let's see what would happen if they were involved in some real-world accidents at higher than regulatory speeds.
The 690-ton concrete block at 60 miles per hour. It was cleaned up and impacted a second time, but at 84 miles per hour. The cask also survived this more violent crash with only minor damage.
That was what's left of the impact limiter.
In the third test, a diesel locomotive crashed into a truck at 81 miles per hour. The stalled truck carried a 25-ton shipping cask.
It takes a little bit to accelerate a locomotive.
Cask deformation was minimal, and the ability of the cask to contain and shield its radioactive contents was not compromised. The final impact test had a 74-ton shipping cask carried by a cask rail car crashed into the concrete block at 81 miles per hour. The same cask and rail car were then positioned over a pool of jet fuel and subjected to an engulfing fire, much more severe than the fire that might occur in a train wreck. After 90 minutes, 3 times the duration of current qualification test criteria, surface temperatures exceeded 1400 degrees Fahrenheit, but inside the cask, where the spent fuel rods would be contained, temperatures were below 300 degrees. Not enough to melt the spent fuel rod.
So as you can see, there are even a few funnies in the film itself. 300 degrees, not enough to melt the spent fuel rods. I don't think you're going to melt uranium oxide in a fuel rod at anything approaching those temperatures. But that just gives you a flavor for the extra regulatory tests that were done. At 60 miles per hour on a truck, at 80 miles per hour on a truck, and at 80 miles per hour being hit sideways by a locomotive, the damage that was done to that was less than or the same as what was done in the regulatory test. Now, the tests themselves have actually, they've been criticized as not being severe enough. And to air the criticisms, you know, to be honest about what people said about it, this was an obsolete cask, so it's an invalid test. Well, DOE didn't have enough money to go buy $1 million new cask, so they used an obsolete cask, but it was built to the same standards that modern-day casks are. As I mentioned, the regulations have changed. They've evolved over the years, but the same basic 9-meter drop onto an unyielding target hasn't changed. The rail crossing, this one was criticized because the cask was not set low enough to hit the drawbar of the locomotive. And part of the reason was they artificially lowered the trailer, I forget some amount, 6 or 8 inches, to get it down to where it would hit the frame of the locomotive. If it had been a normal grade crossing, the frame and everything would have gone under the cask. So they lowered it artificially, but they were criticized for not lowering it enough. You know, you didn't lower it far enough that it would be the absolute worst case. So that even when tests like these are done to validate the adequacy of the regulations and the codes and standards that are used to predict cask behavior, and some people just remain unconvinced.
Only a full-scale rail crash would really prove the point. So, in July 1984, CEGB organized Operation Smash Hit. The same flask as was used at Cheddar was fitted with a new lid, filled with a ton of water and 200 steel bars once again to simulate uranium fuel rods, festooned with measuring instruments, and mounted on a British Rail flat row, the kind of wagon used for transporting operational flasks. This was then derailed and turned on its side on a stretch of British Rail test track at Old Dalby in Leicestershire, as if it were a real accident. The train was set in motion without a driver. Eventually, it reached 100 miles an hour. It plowed head-on into the derailed flask and wagon. The drawhook on the front of the locomotive hit the edge of the flask, but the lid stayed bolted in position. There was some scarring of the steel and buckling of the outside cooling pin. But the flask had been pressurized to 100 pounds per square inch before the test, and measurements taken afterwards showed that only 0.26 of 1 pound of pressure had been lost, proof that it had remained intact and totally safe for the public had it contained actual radioactive material.
And so, in this case, they actually did position the cask so that the draw hook would impact it. And to do that, they had to lay it over on its side. So it wasn't so much a grade crossing as an accident into an accident. And even there with the UK design, these are solid steel structures rather than sandwich structure, they had no loss of pressure, even though they had pressurized the interior in order to provide them with an easy leak detecting mechanism. So, will the studies and the tests convince people that it's safe? Well, let's be honest, much of the information is just too technical. The risk assessments that are being done is very difficult to communicate that effectively. The experience to date has been exemplary in that there have been thousands of shipments worldwide. There are shipments of spent fuel through Europe all the time, between Europe and Japan. There have been, hundreds of shipments in the United States. So there's a lot of experience. There have been no deaths or serious injuries due to the nature of the radioactive material, but a lot of people still remain unconvinced that something like the transport of spent fuel can be done safely. And oftentimes people ask questions qualitatively, is it safe? Engineers and regulators are reluctant to give them a qualitative answer, such as yes or no. It needs to be, they tend to feel like it needs to be more quantitative and defensible. And as it ends up, I believe we have a dialogue without communication. But in the end, transport safety may not be the real issue. It may be a peripheral issue, but I think it also is going to boil down to the agendas that are at stake. There's both the pro-nuclear and the anti-nuclear movement, and transport safety will get caught right in the middle. And I think the only answer really is for concerned citizens to take the time to become informed, because there's a lot of information out there, but it just takes some effort to get it and to understand it. Thank you.
Okay, we have any questions? Wesley?
You said you had like your 4 points. I think one of the new points today is security of transporting these things. What kind of studies being done now? I'm sure there are plenty of people that want to give you ideas.
There were some studies done in the 1980s where they actually put, they fired explosives into spent fuel rods in a laboratory setting. They did some shake charge insults on actual casks with uranium dioxide, but not spent fuel, fresh fuel. And they did characterization of what those weapons did to the cask. Basically, it would penetrate the cask, made a, relatively small hole at the top. It penetrated, I think, at least half of the fuel rods themselves, and then it made a small hole at the bottom. But then there was no driving force to drive the content out of the cask. So you had a cask sitting there with a hole in it. Those studies were done years ago. As you pointed out, there's much greater focus today on other types of acts. People have pointed out that the weapons now are more sophisticated. The cask designs are slightly different. And so there is a series of studies that's being performed in the United States, in Germany, I think in France also. There's a coordinated program to perform more of those types of tests to better characterize that. So it is being addressed.
Thinking the unthinkable, what about coal shipments? In other words, there could be a large chemical company that produces radioisotopes but also produces chemicals, and at the same time corrosive chemicals. Regulations covering coal shipments, in other words, it could very well be that accidentally corrosive chemicals end up in the same shipment with radioactivity.
Well, corrosives probably are not too bad because of the slow time or the long time it would take for them to adversely affect the packaging. But other things such as explosives, liquid energy gases, flammable liquids, those types of things are addressed in the carrier requirements. And so there are some segregation requirements to where you can't put two hazard classes of materials together. So those are included in the U.S. regulations. But that is addressed.
Would that be criminal if they did expose?
They did it knowingly.
Art?
I think the main effect of showing people the billions that are spent and the incredible durability of this transportation can, to reinforce in their mind that this material is incredibly dangerous. It's extremely counterproductive.
Yeah. That is somewhat of a loop.
The airline industry understands that. I mean, they tell you that if you land in the water that your life jacket is deep. They don't have to pull it out, put it on, think about all that water around the aircraft. So, we need to save some people. That $10 million they're spending is not going to be directed at technology.
Tom?
Nevada seems to be making a lot of static. I wonder if you could indicate or how much time has been spent on this Yucca Mountain area, and how much money has been spent over that time in developing that facility.
Well, they've been studying it for a long time, and if I'm not mistaken, I think the number that I heard bantered about was $3 billion, and 20 years of study.
And they're just now complaining.
Well, it's just gotten into the political process in such a step that it's actually moving forward. While it was being studied, it was just in the study phase. But once the Secretary of Energy accepted the study results and recommended to the President that it go forward, that started this next phase of the political process that was put in place by the Nuclear Waste Policy Act. Then the President approved the recommendation from the Secretary and sent it to Congress. That was the next step in the process. Nevada has, or whichever state the site is situated in, has the opportunity to veto that recommendation, which they either have or they're going to. It's a slam dunk. And then Congress has to override that veto within 90 days that they're in session. But there's some rules that are set out in the Nuclear Waste Policy Act that govern that process. So it's started in the last couple of months.
It seems kind of ridiculous if we've been going at this for 20 years, spent $3 billion, and now we're making such a stink about it.
Well, the state of Nevada has been against it the whole time. It's not a new thing. They've been...
They didn't object to spending all that money over the last 20 years.
Well, they were actually
They've been against it ever since.
They had no choice.
Their congressional leadership has been leading the fight against all of the DOE activities there in trying to characterize the site.
Well,
You mentioned temperature limits of 800 degrees Celsius. Don't they test for specific things?
Temperature.
They test for that kind of temperature. What kind of?
how do they determine this?
Well, the temperature was based originally on characterization of accidents. Then when it's translated into the engineering specification, that can either be done in a fully engulfing pool fire, but the fire has to be just the right size. It can't be too small to not be fully engulfing. It can't be too large to generate oxygen starvation in the center, which would not result in a hot enough temperature. The package has to be located over the pool so that it is in a situation where it will get radiated heat on all of its sides. So it's somewhat of an artificial scenario to ensure that maximum heat goes into the package. But it can either be done with a hydrocarbon fire or a furnace test. And many of them are done in furnaces these days.
Any other questions?
Sort of interesting, the latest car company which shows crash tests on TV, I think it's Subaru. I think I saw it. I don't know, maybe there are not enough crash tests like that shown on TV. That's the other side of the coin, because somehow the public seems to be influenced by crash tests, because car manufacturers would not show that if it wouldn't impact on sales.
Those tests
And they're spectacular. I mean, this is nothing.
Well, they both the U.S. test and the U.K. test generated about a day or a day and a half of coverage. You know, it would show a clip on the news or so, and after that, the world moved on and the tests
Yeah, well, I didn't mean that so much. It's just, you know, they seem to be selling products like cars by showing crash
based on crash resistance.
And so, in a way, I don't know, we could sell this.
Have you seen the latest Mercedes crash test on TV for Mercedes?
I'm not sure.
The car goes through the target, out of the building, and on into the parking lot. And then they show you the car, and it's in essence, it hadn't been damaged.
I haven't seen that.
The toughest SUV.
Yeah, toughest SUV on the road. Okay, we can have more questions and comments downstairs in our refreshment time. Some of you are new here, new faces, and you don't know that we do have refreshments down on the second floor, and everyone is invited. But before we adjourn for refreshment, let's express our appreciation again. Yeah, your voice is fine. Let's go downstairs and, because I'm sure you will get some more questions and comments. Uh-oh. You're the freshman. Or no, you're a chemical engineer, right? Right here.
Very interesting. John,